Okay, so I think we can start now. It's my great pleasure to introduce Elkin Quintero Vanegas from Federal University of Amazonas from Brazil. And he will talk today about Albert's problem and its connections. Okay, please, you can start.
Thanks, Artem. Okay, firstly, I would like to thank the organizers for the invitation to speak in the seminar. And I will speak about the Albert's problem and its connections. And we will go that this is just a classification problem of algebras. So if we are studying a class of algebras, it's interesting to study their simple objects. And for any algebra in the class of algebras, uh, uh, it's interesting to study the irreducible and the decomposable models. So the talk is about that connection between simple algebras and the Albert problem. So I will initially to speak about the power-associative algebras. I will introduce the Albert problem and irreducible models. After that, I will speak about the irreducible models over the zero algebra of dimension 2 and the irreducible models over other kind of algebras. And finally, I will give an equivalence to the Albert's problem using irreducible models. So fixing some notation, F will be a field of characteristic different from 2, 3, and 5. Occasionally, F will be an algebraic closed field, but for the general case, it's now to be different to 3 and 5. A will be a finite dimensional algebra over F, and AN will be the zero algebra of dimension n. It means it's just a vector space of dimension n with zero product. And finally, the associator among three elements. So in the general case, for non-associative algebras, there are different ways to define the powers of an element. I will be use the right principal powers inductively as x to power 1 is just the element x, and for any k greater or equal than 2, we define x to power k plus 1 as x to power k times x, and some powers of the algebra that we will be used are the following. A to power 1 is just the algebra A, and for any k greater or equal than 2, A to power k plus 1 is the sum of all the integers a plus j being k plus 1 of the subspaces a to power I times a to power j. Another power of the algebra that will be used is the following. A to power parenthesis 0 is the algebra A, and for any k greater or equal than 0, A to power parenthesis k plus 1 is the multiplication between A to power parenthesis k times A to power parenthesis k. So if we have that for any x in an algebra, there exists some integer greater or equal than 2 such that x power k is 0, the algebra is called a nilalgebra. And if there exists a general k such that for any x, x to power k is 0, the last k is called the Nil index of the nilalgebra A. Some definitions about the algebra A, we will say that A is nilpotent if there exists some integer k such that a to power k is 0, and the algebra is solvable if there exists some k such that a to power parenthesis k is 0. So what is a power associative algebra? If we have an algebra when the subalgebra spanned by X is associative for any element X lying in I, the algebra is called a power-associative algebra. And the principal motive for the characteristic to be different to 2, 3, and 5 is due to this theorem. If we consider a commutative algebra over a field of characteristic prime with theory, then A is a power associative if and only if A satisfies the identity x squared times x squared equal to x to power 4. And it's clear that power associative algebras are generalizations of Lie, Jordan, and many other class of algebras. And we have the following picture. If we have that every 3 elements in an algebra span an associative algebra, we have an associative algebra. If we have that any 2 elements in an algebra span an associative algebra, we have an alternative algebra. And we have that every element in the algebra is spanned an associative algebra. We have the power associative algebras. And in the case of commutativity, we have the identity in terms of the commutator. So in the seminal work about power associative rings, Albert asked about the nilpotency of the algebra. If we consider a finite dimensional commutative power associative algebra, nilalgebra, A is nilpotent. More than 20 years after Albert asked it, Suttles in 1972 present a commutative power associative nilalgebra of nil-index 4 and dimension 5 is spanned by A squared, A cubed, B, A squared times B, and the non-trivial products being B times A cubed equal A squared, and A times A squared B equal minus A squared. So here we have an algebra such that A squared is equal to A to power K for any K greater or equal than 2, and it's the space spanned by A squared, A cubed, and A squared times B. However, if we consider A to power parenthesis 2, it satisfies that it is 0. So it's a nil algebra, which is not nilpotent, but it's solvable. So the Albert's problem remains as the following. Let A be a finite dimensional commutative power associative nil algebra. A is solvable. The interesting of this equation is the following. If we have negative answer for this problem, it's equivalent to the existence of simple nil algebras in the class of commutative power associative algebras. If we suppose that simple nil algebras exist, then A is not solvable because A squared is equal to A. On the other hand, if the Albert's problem is false, take A with minimal dimension. It means A such that the dimension is the less about all the non-solvable algebras. A results in a simple algebra because if there exists a non-zero proper ideal of A, but I and A quotient by I are the dimension are less than the dimension of A, So by hypothesis, they are solvable, and it concludes that A is solvable too. So it's not possible to that ideal exist. So the Albert problem was studied in two ways until 2001, 2011. The first way was fixing the dimension of the algebra. In this case, for algebras of dimension less than or equal than 9, the Albert problem is true. In this case, we need the characteristic of the field being 0. Or for dimension less than or equal to 8, the characteristic will be different from 2, 3, and 5. And the other way is fixing the nil index of the algebra. In this case, for algebras of dimension n and nil index greater or equal than n minus 3, the Albert problem is true. In this case, the characteristic must be different from 2, 3, and 5. So the first relation between the Albert's problem and irreducible models is due to Ivan Shestakov. If we consider a zero algebra and M an irreducible A model in the class of commutative power-associative algebras, if there exists a map B from M times M onto A, such that the extension A plus M is a commutative power-associative algebra, where the product is defined in the following way. So we have that A is zero product, so A times B is 0, but we have the application B calculated on M times Mn plus An plus Bm. That part belongs to the model, and that part belongs to the algebra. With that considerations, E is a simple nil algebra. So models over a general class was introduced by Ellenberg, in general by models over a class M. If we have A, an algebra over a class M a vector space, and T and S two bilinear maps with domains A times M and M times A, we say that M is a bimodule of A in the class M if the null split extension A plus M belongs to the class M, where the product in the null split extension is defined as A times B, the part belonging to A, and the part belonging to M is defined by the applications S and T. First, T applied in A, M2, and S applied in M1, B. So our interest is to study the commutative power-associative algebras, and over a field of characteristics different from 2, 3, and 5, the identities are xy equal yx and x squared times x squared equal x to power 4. And due to the commutativity, the applications S and T are equal, and we will denote just by L, the left operator. So we have the theorem that the algebra A constructed by Shestakov gives a negative answer to Albert's problem. So this theorem indicates that it's interesting to study the irreducible models over zero algebras. And now consider M4, the subclass of the commutative power-associative algebras. In this case, we fix the nil index as 4. If we take an algebra in the class M4, if A squared is a subset of the annihilator of any irreducible A module over the class M4, then the Albert problem has a positive answer. And the proof is clear if there are simple nilalgebras, set A one of them. Thus, A is an irreducible A module, but A squared is not 0, and 0 is the annihilator of the algebras. So Albert's problem must be a positive answer. Interesting that in the latter theorem, the condition of the nil index is necessary because there exist irreducible modules such that an annihilator of the module is 0 for algebras of nil index 5, but A squared is not 0. If we consider the four-dimensional algebra spanned by A, B, A squared, A times B, such that B squared is 0 and A cubed is 0, if we consider M, the vector space spanned by V1, V2, V3, V4, and V5 with these relations here, and this zero product, we have that M is a commutative power-associative irreducible A module. The annihilator is 0, but A squared is not 0. So in this theorem, the condition of nil index 4 is important. So we have the next conjecture. Let A be an algebra of nil index, let's say quote on 4. If M is an irreducible A module, then A squared M equals 0. And suppose that the above conjecture is true, then there exists a bijection between the irreducible modules of A and irreducible modules of A quotient A squared. It's possible to construct for any irreducible module of A quotient A squared, it's possible to construct an irreducible A module acting A squared as 0, but the conjecture here gives the equivalence. So what is the knowledge about the irreducible modules? Almost nothing. Now F will be an algebraically closed field to the rest of the talk. Firstly, the modules for A2, the zero algebra of dimension 2. We have that M is an irreducible module in the class of the commutative power-associative algebras, if and only if the dimension of the module is 3. And in this case, there exists a basis of A, AB, and a basis of M, V1, V2, V3, and a non-zero scalar such that the action of A in this basis is given in this way. Furthermore, if delta is the set of eigenvalues of the application LA, LB, and the quantity of elements of that set is greater than 1, then M is a decomposable model. So the irreducible modules for A2 are determined, but what about the irreducible modules for AN? The one thing that we have is that if M is an irreducible AN module, then M is an n+1 irreducible model. And we will use the irreducible models of the Lie algebra SL2 to construct some irreducible models for the zero algebra of dimension 4. So we know that every irreducible mod SL2 model of dimension 2 has this picture. The action of A goes for the right, the action of F goes for the left, and the action of H is scalar. And this picture helped us to construct irreducible models for the zero algebra of dimension 4. If we change each vertex by the irreducible model of dimension 3 of the zero algebra of dimension 2, we need just in a convenient way give the action of the algebra of dimension 4. So in this case, it's possible to construct at least two families of non-isomorphic irreducible models of dimension 3n for any n greater or equal than 2. And for n equal 1, there exists an irreducible model of dimension 3. It's the irreducible model for the zero algebra of dimension 2. And the picture for this model is similar like the picture for the irreducible model of SL2. But we have here an element that goes for the right, in this case, C, with this action. And all of them are graded subspaces. In this case, the action of C is 0. And in the first case, the action of D, that D goes for the left, is 0. But they are down in the level in each graduation. This gives us an irreducible model for the algebra of dimension 4. Note that here we have the irreducible model of dimension 3 for the zero algebra of dimension 2. In this case, the algebra is defined by A and B. And we need the elements C and D for goes to the right and the left. Here we have the algebraic structure of that model. It's interesting that we have n parameters for this model, all of them being different to 0 to be irreducible. So the family is parameterized. And if some scalar is 0, we have a decomposable model, but not irreducible. So we need all scalars being different to 0 to be irreducible. And another family is similar like the first one, but in the first graded space and the last graded space, it changes a little bit the action. Here is the picture. In this case, the first graded space goes to the right by C, but goes to the left by D. And in the first case, D is 0 in this subspace. But now D goes for the first graded subspace to the last graded subspace. And analogously with C. C goes for the right. In the first case, in this graded space, C goes for 0, but here C returns to the first subspace. So we have in this case like a ring, a model ring, and here we have the algebraic structure. In this case, we need here that all the scalars, we need n+1 scalars, and all of them must be different to be irreducible. If we have that there are equality in two of them, the model is not irreducible, but is indecomposable. And what about non-zero algebras? If we have an algebra such that a squared is not 0, consider first M an irreducible A model such that there exists an application M to M times M into A, and we define the algebra QM as the vector space A plus M, but the product now is the following. Product here, A times B is not 0, and we have the application M, so the part of the algebra A is A times B plus M calculated on VW, and we have the action of A in W and B acting on V. So AW plus BV belongs to M. And consider the canonical projection to A from A quotient A squared. In this case, we have the following equivalences. The Albert problem holds there are not simple commutative power-associative nil algebras, and given commutative power-associative nil algebra, M an irreducible A model, if there exists an application M such that Qm, this algebra, belongs to the commutative power-associative algebras, then the composition pi with M is not onto. So the condition to the Albert problem holds is due to this composition is not onto. And another way that we are exploring is to connect nil algebras with another class of algebras, in this case with Maltsev algebras, with the idea to connect with the Albert's problem, but we are exploring that way. If we consider an algebra over the class of commutative power-associative algebras of nil index 4, remains that 4 means that, and element A belonging to A such that A squared is 0. So for any Y and Z in the algebra A, we have this equality where X, Y, Z means the application, the left application Lx, Ly applied in C. So this expression is well-known defined. So in this case, if we define a new product over the vector space A in the following way, Y times Z being 1/2 of YC plus YAC plus YAAC, This product defines a Maltsev algebra, and that Maltsev algebra depends on A, because A must be satisfied that A squared is 0. And some interesting properties about that algebra are the following. If A is an associative algebra, we have an abelian Lie algebra. If A is Jordan, we obtain an nilpotent Lie algebra of index 3. And in the general case, if A is commutative power-associative algebra of nil index 4, we have that the Maltsev algebra is nilpotent and its solvable index is less or equal down 3. So we are exploring the connection between the commutative power-associative algebras with Maltsev algebras or any other class of algebras to explore the Albert's problem in other contexts. And some conclusions are the following. If we have the zero algebra of dimension 2, we know that there are only one irreducible model, so its multiplicative enveloping algebra is finite dimensional. But for any n greater or equal than 4, there are families of irreducible modules. So the multiplicative enveloping algebra of an is infinite dimensional. And the question is, what about A3? Until now, we are exploring the irreducible modules of A3, but we have not concrete results. And it's there are some reference that I have used to this talk. And thank you so much.
Thanks a lot for your talk. Okay, so are any questions, comments, observations? Okay, so I have one question. So, as you said at the beginning of your talk, one of the purposes, one of our motivation is to find out some nil simple algebras, yes? Or to
Yes.
classify, yes, to better to say, to classify nil simple algebras, which may be power-associative commutative, maybe not, I don't know. And so, do you have some, I don't know, examples of nil simple algebras, maybe some new examples here?
In this case, the class is the commutative power associative algebras. So until now, there are not samples of that kind of algebras. I guess that there are not exist, but there are not approved, and until now, there are not examples that show a simple nil algebra in the class of commutative power associative algebras.
Okay, so at the moment there is no such examples are known, yes?
Yes.
Okay,
Yes.
and mhm.
That is the interest of the equation. Just because the Albert problem is false, we have the existence of simple nil algebras. But if the Albert problem is true, that kind of simple algebra does not exist.
Yes, but I mean in some cases, Albert for some fields, Albert problem doesn't hold, yes? And so in this case, we still don't have example of nil power associative commutative algebra, which is simple. Yes.
No, yeah, yes. Until now, it's we don't know one example of that algebra.
Okay. It's
We
interesting.
have examples of nil algebras which are not nilpotent. but solvable is until now every new algebra is finite dimensional, of course, is solvable.
Mm-hmm. Mm. Okay. Okay. Are any other questions or comments? Okay, then let's thank the speaker again for his interesting and detailed talk.
Thank you, everyone.
Okay, thank you. Okay, Azamat, do you have some comment? No? I guess not. Okay. Are any other comments? No? Okay, then that is it. I guess see you on the next week. Okay.